We can start with trial and check. If p equals 7, that gives us p to the fourth minus 1 equals 2,400. Unfortunately, that doesn't help because all of the answer choices are factors of 2,400. So instead, we try p equals 11. If we try p equals 11, then p to the fourth minus 1 becomes 14,640. If we look at that, you can see that it's not divisible by 150, it's not divisible by 180, and it's not divisible by 400, so that narrows our answer choices down to A and B. You could keep checking more numbers, and the more numbers you get, the more you see that they are divisible by 120 and 240. So you suspect that the answer is D, but you want to prove it. And the way to do this is to factor the polynomial p to the fourth minus 1. We know that it's a difference of squares, and that will factor into p squared plus 1 times p squared minus 1. But p squared minus 1 is also a difference of squares, so we still have the p squared plus 1, but p squared minus 1 factors into p plus 1 times p minus 1. Because p is a prime number greater than 5, we know that p is odd. That means that p plus 1 and p minus 1 are both multiples of 2. And in fact, they're consecutive even numbers. That means one of them is divisible by 4. So that's another factor of 2. Also, p squared plus 1 has to be an even number, so that's also divisible by 2. That means that p to the fourth minus 1 must be divisible by 2 to the fourth power, or 16. Next, let's consider the consecutive integers p minus 1, p, and p plus 1. Anytime we have 3 consecutive integers, we know that one of them is divisible by 3, but it can't be p, because we know that p is prime. That means p minus 1 or p plus 1 is divisible by 3, which means that our original number, p to the fourth minus 1, is also divisible by 3. My last claim is that p to the fourth minus 1 is going to be divisible by 5. We might guess that from the first two examples above, where we got 2,400 and 14,640, but we want to prove it. Because p is a prime number greater than 5, we know that its ones digit is going to be 1, 3, 7, or 9. Now let's look at p to the fourth minus 1, specifically in its factored form. If p is a number that ends in 1, that means that p minus 1 is going to end in 0. That means that it's a multiple of 10, which means that it's a multiple of 5, which means that p to the fourth minus 1 is going to have a factor of 5 somewhere. So it's going to be divisible by 5. Similarly, if p ends in 9, and we look at p plus 1, that has a ones digit of 0, so it's a multiple of 10, which is a multiple of 5, and that means that p to the fourth minus 1 is also a multiple of 5, which we wanted to prove. Lastly, if p ends in 3 or 7, then p squared plus 1 is going to be a multiple of 5. For example, 3 squared is 9, plus 1 is 10, 7 squared is 49, plus 1 is 50. However it ends up, this is going to end up being a multiple of 10, which is also a multiple of 5, which means that p to the fourth minus 1 will be a multiple of 5. So in all of the work that we've done, we've seen that p to the fourth minus 1 is divisible by 16, 3, and 5, and if you multiply all of those together, you can see that p to the fourth minus 1 is divisible by 240, which is answer choice D.